Good morning, good afternoon, and good evening, everyone. This is Horeya Ismail, my master's degree in public health, major in Biostatistics from Alexandria University in Egypt. I'm speaking to you today on behalf of my team, Prime for Integrated Research Solutions. My colleague, Dr. Nermina Osman, is a lecturer of medical statistics at the Medical Research Institute in Alexandria University, will brief us about our network, Prime for Integrated Research Solutions.
Hello, welcome everyone. It's my pleasure to be with you today. I would like to speak about the mission and vision of our company, Prime for Integrated Research Solution, which is an integrative site network for biomedical research consultation. We have a team of research professionals offering support in statistical analysis and medical writing. We work in person and remotely to offer integrative research service specific to the needs of our researchers. We love what we do and have dedicated to research, and we care about the success of young researchers and sustainability and the growth of research groups we work with. Our mission to provide high quality research services and to facilitate the study logistics so that researchers can learn from the provided services towards their research career. And we have a mission of disseminating statistical knowledge among academic students and young researchers to enhance their abilities and qualification to implement the research. Our vision to disseminate our knowledge to the professionals and clinical research. Thank you very much.
Today is a very special day to us. We have a very special guest speaker, Professor Gareth James. He is a professor of data science at Southern California and Morgan Stanley Chair in Business Administration. He is a professor of data science and operations and the dean of MSc Marshall School of Business. He is elected, got too many honors and awards. He is elected as a fellow of the Institute of the Institute of Mathematical Statistics, and the associate editor for the Journal of Royal Statistical Society, and he is the first author of the brilliant book, An Introduction to Statistical Learning with Applications in all. Really, in the current days, data is the language of the world. Statistical learning has become a critical toolkit for anyone who wants to understand data. The brilliant book, An Introduction to Statistical Learning, turned the most technical subjects in statistics into understandable and even enjoyable field. Really, thanks to the authors of this brilliant book, it should be on the bookshelf of any statistician and anyone wants to intelligently analyze data by modern statistics without requiring a background in mathematics and statistics or computer science. Professor Gareth James will give us an overview about this brilliant book and the updates in the second edition. Welcome on board, Professor James, and welcome all of the audience.
Thank you. Thanks for the invitation to present to this group. So I think the idea of the presentation was to give a little bit of an overview of the Introduction to Statistical Learning book that I co-authored with Daniela Witten, Trevor Hasty, and Rob Tipsharani. And then that's the second edition of the book just came out a month or two ago. So a little bit of an update on what the new material is in the new version of the book. So the story for this book actually originates back prior to 2013 when the first edition was published, and it goes back to the Elements of Statistical Learning book, which was a very popular book published first in 2001 that Trevor and Rob published with Jerry Friedman, and it's been one of Springer's top-selling books in statistics, and it's because it was one of the first books to lay out the foundations and theory of some of the modern statistical approaches. It covers models, fitting criteria, and optimization algorithms, and theoretical properties of these methods. And the book, as I said, was very popular. It had a large audience, but it is a pretty high-level book, so it's really for PhD in mathematical sciences sort of level. So the book does have a limited audience because of that. So when we got together to write this new book, we had a premise that there was actually a much larger audience for these sorts of methods, and that software had now advanced to the point where a lot of these really advanced statistical approaches would become as common to implement as other standard statistical approaches like linear regression and such like. And that there was an audience out there for these methods that had a moderate statistical and mathematical training, but didn't need as technical a guide as most statistical books go into. Didn't need all this sort of theoretical development. Even some of the algorithmic development was unnecessary for these people, but that they did need to understand some of the basics, some of the models, some of the ideas behind these methods. So that's what led to, in 2013, the publication of ISLR, the Introduction to Statistical Learning with R book. And there were 4 premises behind this book that we tried to keep to when we were writing the book. So the first was that many statistical learning methods are relevant and useful in not only academia, but also outside academia. And I've really been interested to discover all the different areas where this book and these methods in particular have become very popular. So for example, in the financial industry, I've done some consulting workshops and things like that for hedge fund groups that wanted to understand these methods better. So that premise seems to be quite accurate. The second was that at the time of the publication of this book, there were a lot of people applying these methods that were just using them purely as a black box. They would get some kind of result out, but have absolutely no idea how the result was produced, and hence no idea of whether they had any kind of reasonable result. So we didn't want these methods to be viewed as sort of a black box, something that pops out of a box. On the other hand, while it's important that they know how each cog in the box works, so they know the basics of the method, in other words, it's not important that they know how to make the box, how to produce the method, how to code things up, or even necessarily the algorithms behind the fitting procedures. So we were trying very hard to give people the basics, the intuition of these approaches, and a little bit of the introductory math, but not go into too much detail. And the final one was that we presumed that the readers were interested in actually applying these methods in real world settings. So that was sort of the premises for writing the book. It turned out to be a popular book, got high ratings. And if you look at, even this weekend, I had a look on Amazon's bestsellers in AI, and 3 of the top 6 bestsellers as of this weekend were the Elements of Statistical Learning book that Trevor, Rob, and Jerry wrote, and the first and now the second edition of ISLR. So clearly it's still receiving a lot of attention. So what were the keys to the success of the book? I think there were a couple of reasons that it was successful. Obviously, timing is important, but as I mentioned, we worked very hard to avoid unnecessary mathematical detail. So if you have a look at the book, you'll see that there's a lot of pictures, a lot of diagrams, sort of intuitive ideas behind these approaches. We do have formulas and such like in the book, but we try to minimize those to make sure it's only sort of the most necessary ones that are in there. And then another big factor in the success of the book, I think, was the fact that at the end of each chapter, we had an R lab where we went through in great detail how to actually implement the methods in that chapter using R. And I think that was very popular with a lot of people because they could actually see how to use these methods once they'd learned about them. So here's sort of a partial summary of the topics that were in the first edition of the book. We started off with a little bit background on the bias variance trade-off, which I think is very important for these very, very flexible statistical learning approaches. The concept that as you make a method more flexible, the bias is going to go down, but the variance will go up. So eventually your error rate will start to go back up again. A quick review of linear regression, then on to some classical classification methods like logistic regression, LDA, k-nearest neighbors. And then the next part of the book, the rest of the book really was on more modern approaches. So we started talking about resampling ideas, cross-validation, bootstrap approaches, things like that. On to shrinkage methods, ridge regression, lasso, principal components regression. And then moving on to non-linear regression methods, some classical, but also many modern methods. So splines, local regression, bagging, boosting, support vector machines, random forests, methods like that. And then the final chapter in the book is on unsupervised learning approaches. So we talk a little bit about principal components analysis, some clustering methods like k-means and hierarchical clustering. So that was the first edition. It had 10 chapters in it. And then a couple of years ago, we sort of got together and we decided that there was some material that was now missing or out of date in the first edition of the book. Some of that was material that maybe could have been in the first edition, but we didn't put it in. Other material like deep learning, for example, was not even really on the radar in 2013 when the first book was published. So we worked to start writing material for a second edition. And as I mentioned, a couple of months ago, we finally got that second edition published. And so I just wanted to sort of talk a little bit about what's new in that second edition. And so there's 3 new chapters in the book, one on deep learning, a new chapter 10, one on survival analysis and censoring, that's chapter 11, and then a brand new chapter on multiple testing problems, multiple hypothesis testing, which is chapter 13. And in addition to those new chapters, there's also about 4 new sections in the book in some of the current chapters. So one on matrix completion and recommender systems, one on naive Bayes, one on Poisson regression and the general concept of generalized linear models themselves, and then one on Bayesian additive regression trees on BART. So I just want to spend a few minutes sort of summarizing what the new ideas are in these chapters. And then I'm very happy to take any questions or comments people might have afterwards. So first of all, deep learning. So deep learning really wasn't even on the radar of most people back in 2013 when the first edition was published. But of course, it's a very popular and successful approach now, though a lot of people don't actually really know exactly how to implement it. And the sort of starting point for deep learning is neural networks, which have been around since probably the 1960s now. They became very popular in the 1990s, died out a little bit in popularity at the start of the century with other approaches like boosting and random forests becoming more popular. And then sort of over the last 5 to 10 years, they've jumped back in popularity as this concept of sort of deep learning has become such a successful implementation of neural networks. So the basic idea of neural network from the 90s is of a single hidden layer, as in this pictorial representation I have here. Deep learning extends this concept to not just one single layer, but to multiple layers, hidden layers within the neural network. And until recently, it was thought that implementing methods with multiple hidden layers was just not feasible, but advances in computing and algorithmic development have made that both possible and quite successful to implement. So we go through in the book some various different types of deep learning multi-layer neural networks. And one of the most popular is the convolutional neural network, which is, for example, often used for image processing. So here's a simple pictorial example. Here we have an image of a tiger. It's a color image, so there's three parts to it: red, green, and blue. These images get fed into what's called a convolutional step, and then that convolutional step gets fed into what's called a pooling step or layer. And then this is repeated multiple times, a convolutional layer and a pooling layer. And each time it's repeated, the dimension of the image gets compressed down to a smaller and smaller dimension. And eventually, at the end of the network, there's a classification step where, in this case, we're trying to classify what type of animal is this an image of. So we go into detail on how to implement these convolutional neural networks. We also talk a little bit about document classification, how deep learning can be used for document classification, and then move on to recurrent neural networks. Now, recurrent neural networks are another interesting deep learning approach that's used in a setting where you have outcomes in a sequential basis. Now, that might be a time series basis, it might be words in a document. Financial time series is another example of recurrent neural networks. So we show how deep learning can be used to fit these. Talk a little bit about time series forecasting and deep learning in relation to time series forecasting in particular. And then the last topic we talk about in this chapter is this idea of double descent. So for those of you that might have read the first edition of this book or other books or papers in this area, you know that there's a common assumption that as you make a method more flexible, you'll sort of see a U shape in terms of the error rate, that it goes down to start with and then starts going back up again as the variance in your estimator dominates. More recently, people have found certain situations where you actually get sort of a double dip, where you get this U shape where the error rate goes up, but then it starts to go back down again, at least for a while. And I think there's a lot of confusion about why that is the case and what's causing it. So we talk a little bit about this book, and I think provide a relatively intuitive explanation about how this can happen, and that it's not in fact a violation of this bias variance trade-off idea. It's just that you need to think about these concepts a little more carefully. This was a very hard chapter to write because deep learning is just frankly not an especially easy method to implement or to understand. The lab at the end of the chapter, I think, will be very useful for people because it does sort of explain both how to install the software for doing this, which is not so trivial in itself, and then how to implement the deep learning method. So hopefully people who want to experiment with deep learning will find that lab session quite useful to get them started with these methods. Okay, so the next new chapter was on survival analysis. And so we start the chapter with sort of just a basic definition of what a survival curve is and such like, and the related concept of censoring. Kaplan-Meier curves, looking at sort of this, estimating the survival rates for, in this example, males and females with a different disease. The related idea of the log rank test to decide if there's a difference between these two survival curves. And then moving on to doing regression with survival analysis, and the Cox proportional hazards model obviously is closely related to that. So everything I've got here is pretty classical material, though still very relevant and important. But the chapter also talks about some more modern ideas like penalized approaches to do shrinkage on your survival analysis and such like. So relating sort of the lasso and other methods to that. And of course, there's a lab at the end of the chapter as well. And then the third new chapter is on multiple hypothesis testing. And what we discovered is that the audience for the first book was, as I said, not just within the statistics community, but a lot of different communities. And as a result, even some of the sort of more standard statistical ideas like hypothesis testing was not necessarily so well understood by all of the readers of the book. So we start this chapter off with just a very basic review of the concepts behind hypothesis testing, how to perform a standard hypothesis test. Then we move on to some of the problems that you encounter if you have multiple hypothesis tests, you're trying to do more than one hypothesis test at once. So we start by talking about the family-wise error rate, the sort of generalization of a type 1 error to multiple hypothesis testing, and illustrate, for example, with this graph here, how that family-wise error rate can go up dramatically as you have more and more hypothesis tests that you're trying to perform. We talk about some classical approaches for trying to control that family-wise error, rate, like the Bonferroni method, which is very popular, or the Holm method, which is less well known, but is actually slightly more powerful than the Bonferroni approach. Of course, this only works really if you have a relatively small number of hypotheses you're performing. These days, you often have thousands of hypotheses. And so then we move on to some more modern ideas like the false discovery rate, looking at the proportion of all the discoveries you make that are actually false, and trying to control that rather than the family-wise error rate. The Benjamini-Hochberg approach, which of course is very popular for trying to control that false discovery rate. And then at the end of the chapter, we move on to talking a little bit about some resampling approaches. So where you don't have to make these asymptotic distributional assumptions, you can use permutation tests and such like to estimate p-values and even the false discovery rate itself using that approach. So those are the three new chapters. And then, as I mentioned, we also have some new sections within current chapters. So we have a section on matrix completion and recommender systems. So this concept where maybe you observe for each of your customers just a small fraction of all the possible ratings they might give, like the Netflix problem, for example. You might observe 2% of the entries in the matrix and you're trying to estimate all the missing entries. So we talk about just some of the basics of that method. We talk about naive Bayes, which, as the name suggests, is actually quite naive in the assumptions it makes. It assumes that the predictors in your regression are all independent from each other, which is almost never the case, but that naive assumption still can give you quite accurate results. A little bit on Poisson regression and generalized linear models in general. And then finally, on BART, this Bayesian additive regression tree approach, where you combine a whole lot of trees together to get more accurate predictions. So that's just a very quick summary of the book, and I'm happy to talk about any topics that people want to ask any questions on. But just sort of a final summary. So, you know, I think what we've learned from books like this is that there's just a massive audience for statistical learning methods, but not necessarily at the sort of really technical level. There's a lot of well-educated people out there that just want to know how to implement them and some of the concepts behind them, but don't really need to know all the theoretical results. So they need to understand what's inside the box, but not necessarily how to construct it. And, you know, I think one of the takeaways here is that these, as the software develops for these methods, they're becoming more and more easy to implement. And so I think they're going to become just as common as some standard approaches like linear regression or hypothesis testing. They'll just be another tool that people use within their tool chest. Okay, so I'm going to stop there, but I'm very happy to answer any questions people have or any comments that they might have about the book or statistical learning concepts in general.
Thank you very much, Professor James. Really it was very informative presentation and very comprehensive overview about the book. Really, we are so grateful to your time and your contribution with us today. We are very, very excited to have you with us today. Thank you for the brilliant book. Really, it's very, very valuable to anyone and any statistician, and really the book considered our partner in the journey to statistical learning. Anyone of the audience, would you like to involve in the interactive discussion and to give any questions?
Professor James, we are greatly thankful for your presentation. So, you provide us with valuable knowledge toward the deep learning, but we have to discuss the difference between deep learning, machine learning, and artificial intelligence. Could you please provide us with minimal information about their difference?
Sure. So first of all, deep learning is just one method for performing either a regression or a classification problem. Probably most commonly for classification problems, like where you observe an image and you're trying to classify that image into one of maybe a large number of possible groups. So if in that sense, deep learning is a subset of machine learning techniques. Now, the distinction between, so in that sense, there are just a large number of machine learning techniques out there, right? So boosting, bagging, even linear regression, you could consider as a very classical, but still a machine learning technique, or if you like, a statistical learning technique. There's also a question about what's the difference between, say, statistical learning and machine learning. And, you know, the difference is kind of subtle. A lot of the methods are the same between those. I think it's more the sort of the background and thought process behind creating these methods. So both statisticians and computer scientists have been involved in creating a number of these methods. So boosting, for example, came from the computer science literature. Of course, a lot of methods like k-nearest neighbors or linear regression approaches or splines, things like that, came from the statistical community. And the difference between them is essentially sort of what sort of probabilistic background are you putting on them. So statisticians tend to sort of assume some sort of model and come up with an optimization based on that model, and the methods come out of that sort of background. Computer scientists tend to look at this more as from an algorithmic perspective. So boosting, at least in its original form, was mostly sort of an algorithm. It was a very effective algorithm. After the algorithm was developed, then people sort of worked backwards to try to figure out why it was working so well. So that's sort of a little bit about the difference between statistical learning and machine learning. And then there's the sort of term artificial intelligence, which has been floating around. And these terms sort of go up and down in popularity over time. I remember in the 90s when I was doing my PhD, AI was a very popular term and it was taking over. Then at the beginning of this century, it sort of died out, and more recently it's become very popular again. So I think this, you know, the difference maybe between AI and machine learning is that machine learning are these methods which can actually give you predictions, like a prediction for an image or something like that. AI is then taking those predictions and making a decision based on them. So that's the intelligence part of AI, that it's also trying to make a decision. Statisticians tend to not get so involved in the decision-making step. They're more involved in sort of making a prediction itself. And then either a manager or someone else might make that final decision. AI is trying to even automate that decision-making step.
Okay. I would like to ask also, R or Python is more useful for deep learning and neural networking special?
Sorry, can you ask that question again?
R or Python is more useful. Which one of them is more useful?
Oh, for deep learning. Okay, so yeah,
yes,
that's a good question. So, so one of the challenges with writing the deep learning chapter, one of the biggest challenges was writing the lab that's associated with it. And for all of it, there were 4 co-authors on the book, and we all struggled to install the software for running deep learning. So what is the software? So the software is actually both R and Python. So there's a Python version of deep learning, but you can run it from within R. So if you like R, you don't have to switch over to Python. You can actually, we show in the lab in chapter 10 how to implement it using R. But you do have to install Python on your computer to make it run. And so we have actually some detailed instructions on the website for the book on how to do that installation, because as I said, we all had problems with the installation. But I think with the instructions that we put up, it should be relatively simple for people to figure out how to install that software and get it running. So basically, if you like Python, you can use the Python version of it, but if you are used to R, then you can run it all from within R as well.
Okay, from your opinion, what is the prerequisite to be specialized in deep learning?
Well, to be specialized in, I guess I'm not sure exactly what specialized means in this context. To get started using deep learning, you really only need to sort of have prerequisites up to the level of the ISLR book itself. And I saw one of the questions in the comments was, what are the mathematical prerequisites for getting the most out of the ISLR book? And the answer to that is that our concept was that the typical reader of that book would have taken an introductory statistics course, so something up through, say, linear regression, but only an undergraduate level linear regression class. There's no expectation of sort of matrix results or anything like that, or even very advanced sort of calculus or those sorts of results. So the book has been very popular with master's level students, but also upper division undergraduate students. So you really don't need a very advanced mathematical background to understand the book. So I would say that for that deep learning chapter, again, with that sort of background, you could get, you would have enough background to actually be able to implement these methods. Now, deep learning is actually a wide cadre of implementations of neural networks. And I don't claim to be an expert in deep learning, but I have learned a fair bit about it from writing the chapter. And it's very clear that it's still an advancing field. So if you really want to be sort of an expert in that area, you're going to have to sort of delve in pretty deeply. But if you just want to understand it at the level of implementing some of the more standard versions of deep learning, I think, you know, the book provides enough background for you to at least get started on doing that.
Okay, this is great. And what about the topics that will be covered in the next version?
In the third edition of the book?
Yeah, third edition.
So well, we just finished the second edition. It came out about a month and a half ago. We haven't even started thinking about the third edition, but what I can say is that the next version of the book, we're currently in the middle of finishing off a Python version of the book. So we're working with another co-author to convert all of the labs that are currently in R into Python labs, and we hope to have that book out within a year. So I know Python's becoming a very popular approach for implementing these methods as well. So most of the text of the book will be the same as the second edition that we have out at the moment, but all the labs will be recreated in Python for people who want to be using Python. So I hope that'll be useful for people.
This is awesome. So I would like to ask a generic question. What about the challenges that will face the deep learning in the future?
The challenges of implementing deep learning?
Yes. Yeah.
Well, yeah. So again, I don't consider myself a particular expert in deep learning, so I'll confine my comments to the aspects that I'm familiar with here. But I will tell you that that neural networks, and in particular sort of deep learning, has gone through many phases of up and down over the last 50 years or so. So, you know, they were first proposed in the 1940s. The earliest versions of neural networks were theoretically considered. They were better developed in the 60s, but no one could figure out how to actually fit a neural network at that point. By the 90s, computing and algorithms had become sophisticated enough that neural networks suddenly became a very popular approach to implement. Then they died out when other methods seemed to be more successful, like bagging and boosting, random forest, those sorts of approaches. And then again, maybe 5 to 10 years ago, they started to have a big resurgence in popularity as people moved beyond single hidden layer neural networks to multiple hidden layer neural networks. And one of the reasons they were successful is that people were able to create structures around these hidden layers. They weren't just completely arbitrary hidden layers. So I mentioned these convolution steps. for example, in image processing. So I think those architectures, those designs or shapes of the hidden layers are really important to the success of these approaches. And I think that's still an ongoing research area. What are sort of optimal architectures for these different neural networks. And the other really ongoing research area is on the fitting approaches for these methods. So there are all these gradient descent approaches for fitting or estimating the parameters. There's literally thousands of parameters in these deep learning networks. And so the criterion that they're trying to optimize is incredibly non-convex. So in theory, these algorithms could provide just terrible results. They could get stuck in local minima and totally fail to optimize the criterion. In practice, they seem to perform actually quite well, but people are not really entirely sure why that's the case. Why does it work so well? So I would say one of the very active areas of research, at least within statistics, and I think within the machine learning community as well, is trying to understand from a theoretical perspective why these algorithms are still working well, and can we improve on them in any way?
Okay. Thank you, Doctor. We have another question. What is the link between statistical learning and data science?
Yeah, so now we're getting into, again, sort of distinctions over naming conventions. So I would say that data science, that statistical learning, I would call it a subset of data science. So data science, again, probably you've seen some of these diagrams where people try to give their interpretation on data science. I sort of think of data science as the merging of statistical ideas, of computing ideas, and also the sort of communication or implementation of this. So as I said, statisticians tend to be more involved in coming up with a prediction or an estimate, but there's an operations side of this. So in my department, we have a lot of operations management faculty or operations research faculty, if you prefer. And their sort of main goal is trying to take those predictions, those estimates, and actually make a decision in that real world setting. So data science is sort of the intersection of all of those ideas. Statistical learning you might consider as more on the statistical side of that bubble, so making the prediction itself, and then data science is the whole merging of all of those ideas, machine learning, AI, and statistical learning as well.
Okay. Doctor, we have also another question regarding the implementation of neural network in the future of data processing using image or video. What's the future of implementation of data sciences in image or video processing? Well,
so again, I don't think I'm an expert in this area, so I don't want to comment too much on the future. I know that the deep learning algorithms have been very, very successful in image classification. One of the challenges I will say is that it brings up a lot of concerns about sort of civil liberties. So in a lot of different situations, as I know in the US, there's a lot of questions about this, and around the world as well, I think, where images have been used to make predictions about people or other individuals, and there are certainly concerns about are they accurate, are they fair in their predictions they're making, do they make the same level of accuracy for all different groups of people and things like that. So some of the challenges here are not just technical, but ethical and legal implications as well. And so, for example, self-driving cars. So deep learning is one tool that's been used to develop self-driving cars. It's been quite successful from a technical point of view, but there are a whole lot of legal and ethical constraints that are so far preventing self-driving cars in the US anyway from becoming sort of a well-used approach. So it's not just the technical implications, but the legal and ethical ones as well.
What's the implementation of data science using neural network in health economics? Is there a link?
Oh, health economics. So I know that a number of my colleagues in my department are working on healthcare implementations of these methods. So trying to, for example, optimize urgent care. This is with COVID, for example, this has become a very hot topic on if your hospital system starts to get inundated with COVID cases or in a non-epidemic setting, just with the regular patients. How do you optimize the allocation of your restricted number of beds and urgent care beds in particular? And so I know that they've been using some advanced statistical learning, and I think in some cases deep learning approaches to make predictions on, for example, what will the survival likelihood be if a person is put in this urgent care situation versus just a regular hospital bed? When should they be discharged from hospital? What are the trade-offs associated with that, right? So if you have unlimited resources, then you always give the best treatment to every individual person. But as we've seen recently, there are sometimes constraints on those resources. And so how do you optimize those to try to provide the highest quality treatment you can to everyone subject to a limited number of resources?
Okay, I would like to thank you for this fruitful discussion and as a platform with Horeya.
Thank you very much, Professor James. As the current days, as data science is very important career, and there has been a great interest in data science nowadays. So could you please, Professor James, to give us some advice how to advance our career with the fast development of the data science and softwares and statistical techniques? Every day there is a new techniques. Every day there is a very, very fast development in the career. Could you give us advice on how to advance ourselves and what are the top skills every statistician or data science should have?
Sure. So as you quite rightly pointed out, the field is developing very rapidly. There are new methods coming along all the time. So I really wouldn't concentrate so much on trying to keep up with every single new method. My advice is more to concentrate on understanding the core ideas. So the core concepts, bias variance trade-off, for example, is a core concept here. If you understand some of these core ideas, then it doesn't take as long to get the basics of these new methods when they come along. So you may not understand all the details of the new method, but you can sort of relate it to the ideas that you already understand. So obviously, there are a number of technical tools that are important to have a background in the area. So you need to have a certain level of coding ability if you really want to delve deeply into some of these approaches. You don't necessarily have to be a coding genius to implement them. You have to be sort of comfortable with at least coding at the level of R or Python or something like that. Again, though, even if you're not wanting to do that level of implementation, I teach in a business school. We have a lot of MBA students here, and I teach this material to our MBA students who are not coders at all, but they actually find these methods very, very useful to implement. So it really depends on what level you want to get at. Do you just want to be able to implement the methods, or do you want to really delve into the area? A final recommendation, though, is the communication angle. So we have a Master of Business an MS in Business Analytics degree. And for those students, we work very hard not only to give them the technical training, but also teach them how to communicate those results. So when we talk to our industry colleagues, what we find is that they say there are a few people that have the technical skills to implement these methods, but many of them do not have the communication skills to actually work with anyone in business or any of the other disciplines to communicate those results accurately. So the small number of people that both have the intersection of the technical skills and the communication skills are extremely popular, and there's a relatively small subset of those people. So my advice would be to concentrate on both those dimensions, the computing and technical side, but also how to communicate that in a clear fashion to people.
Okay, and when it comes to a student willing to prepare PhD in data science, from your point of view, what are the top 3 skills you look for in a student to work with you?
Oh, that's a good question. So I guess, let's see, if I have to restrict myself to 3, so in no particular order, obviously I'm looking for people that have strong mathematical and computational training. Now, they don't necessarily need to have a deep statistical training, at least at the beginning of a PhD program. Someone who has, so for example, I had a colleague of mine when I did my PhD at Stanford, Emmanuel Candace, who came into that program with an extremely strong mathematical background, and he's a star in the field now. But he knew basically nothing about statistics when he started in the program. So I'm looking for someone who has that background, that sort of, the intellect and background to learn some of these methodologies. So that's number 1. Number 2 is the communication dimension that I mentioned. So I want a student who can write and present in a clear and concise fashion. They can make a logical argument, because frankly, there's no point in developing an amazing method if you can't actually convince people that it's a useful approach. And too many people in these technical areas are able to come up with some great theoretical result, but actually can't explain to anyone how to use these approaches in practice and why they should use them. So that's number 2. And then number 3 is, I guess I would describe it as a drive, as an ambition for success. And surprisingly, a number of students I come across have the first skill. A lot of them have some technical training. Some of them are able to communicate them quite well, but a relatively small fraction actually have the drive or ambition to really be successful in what they're doing. So I guess those are the 3 skills that I would look for most in a successful student. Now, I should hasten to say it's not always obvious which students have those 3 skills at the start, but over time you really learn which students do and which students don't.
Fine. However, regarding medical students or medical graduates from medical universities, don't have the mathematical background or deep background in mathematics. However, the application of data science and machine learning in the biomedical fields is very, very important. Some of graduates of computer science can specialize in applications of data science in medical fields. However, what about graduates from the medical fields and would like to use the application or develop or use machine learning in developing or using the machine learning in biomedical fields without having the basics or the deep mathematics background? How will you advise these students to start in machine learning?
So, I mean, The ISLR book was essentially created for exactly that audience. So these are intelligent people. They have a very strong background in their particular area, but they're not mathematicians. They understand the basics of statistics and such like, but are not trained or interested in developing these really sort of advanced statistical learning or machine learning ideas. But they're still capable of learning the basics of these approaches and how to implement them. So I'm not specifically trying to push my book, but that's the sort of level that the concept behind the book was, that there's a lot of people like the medical professionals that you're talking about, who certainly in terms of intellect have the ability to understand these approaches, at least to the level of implementing them, but really don't need to know the asymptotic consistency results on them. And so that was the premise when we wrote the book, that there was a large group of these people. And I think the success of the book has proven that there are a lot of those people around, and that they can actually implement these methods with just a little bit of help from a book like that. By the way, I'm just putting up on the chat a link to the website for the book. Anyone that is interested, you can download a free copy of the book from the website. So I'm not trying to drive up sales here. The book is freely downloadable from the website.
Yes, we shared the link. Really, it's very, very much appreciated from the authors that they give a free copy, PDF of the book, make it accessible to everyone. And we already have shared this link to everyone to download and benefit from the book. Thank you very much, Professor James, for your time. I don't know if any one of the participants would like to raise any points from discussions. It seems that the time runs, and I highly appreciate your time, and we are really very, very thankful to your time and your effort with us, Professor James.